Hello students, in this video I'm going to solve a question based on isomerism. Welcome to organiChemVerse YouTube channel. As you know, I do videos based on some of the multiple choice questions or interesting questions from organic chemistry, and if you have any doubts or questions you can always post the questions in the comment section. Let's get started. We need to identify what is the configuration of the double bonds for the given molecule and how many stereoisomers are possible for the given molecule. Now, before we start solving this question, first let's understand what are isomers. Isomers have the same molecular formula, but they have different chemical and physical properties due to their structure. It can be due to bond connectivity or due to the spatial arrangement. The geometrical isomers are one of the molecules which have same molecular formula, same bond connectivity, but the spatial arrangement will be different. What does that mean? They can exhibit cis-trans isomerism, that is nothing but configuration of a double bond, or they can even exhibit EZ isomerism. EZ isomerism. What is cis-trans isomerism? When you have a carbon-carbon double bond and it is attached to two different groups, say hydrogen and fluorine, and the other carbon is also attached to hydrogen and fluorine. If the identical groups are on the same side, we call this as cis. Yeah, by now you might have guessed what is trans. That is, if the identical groups are on the opposite side of the double bond, we would call it as trans. So these are cis and trans isomers, and what is the relation between them? They are geometrical isomers. And what do you call the cis-trans? Configuration. So what is the configuration of this molecule? Cis. What is the configuration of this molecule? Trans. Now, let's say if carbon-carbon double bond is attached to four different groups, right? What it means, say we have hydrogen and fluorine, and we have chlorine and say bromine. In that case, we can't do cis and trans. Then we have to do E and Z. For that, you have to follow certain simple set of rules. Many students have this confusion to identify E or Z configuration. They assume that they have to remember for each and every molecule. It's not like that. For any given molecule, for any molecule which you don't know, right? For that you can predict whether it is E or Z. How? By obeying CIP rules. CIP rules are suggested by IUPAC, that is UPAC nomenclature, and it's called as Cahn, Ingold, Prelog rules. What the rule says that on the double bond carbon, if you have two different groups, give the priority based on the mass. The one which has higher mass, first priority. So here fluorine will have higher priority. Between bromine and chlorine, bromine will have higher priority. Now, where the priority groups are opposite to each other. Whenever they are opposite to each other, you have to use configuration E. Why so? Because E is the first letter of entgegen. That means in German they are opposite. They are opposite to each other. That's why we use the term E. Now let's take one more example. So I have hydrogen and fluorine here, and here I have bromine and iodine. Iodine mass is greater than that of bromine, and fluorine mass is greater than that of hydrogen. So where are the priority groups? They are on the same side. If they are on the same side, remember it's Z. Z refers to zusammen. That's in German, they are together. They are on the same side, right? Zusammen. So this is how you give priority for E and Z. Now that you know the rules, we can start giving configuration for double bonds. Now let's start from this double bond, alright. So the carbon is attached to CH2 and CH3, but this in turn attached to a carbon, so this will get higher priority. this side of the double bond gets the higher priority. Now look at this double bond carbon. This carbon is attached to 4 carbons. That means here, including here I'm talking, okay. So this carbon is attached to 1, 2, 3 and of course here 4. Now look at this carbon. This is attached to a hydrogen. So you're comparing hydrogen with the overall methyl. So which one should get priority? Obviously this carbon, right? So they are on the same side. Same side means what do you call this as? This is nothing but Z. Okay, so the first one it is Z. Alright. Now let's move on to this one. There is a hydrogen here. There is a hydrogen. If you have hydrogen, it's actually very simple. You don't have to do the comparison here. The hydrogen are on the opposite side because the identical groups, right? Entgegen. So the second one it is entgegen. Okay, sorry about that. Entgegen. So now let's check for this carbon-carbon double bond. Again, there is a methyl and then there is a double bond here, right? So and what about here? We have hydrogen like this. Okay, so what is the configuration here? They are together. The lower priority groups are on the same side. So it's going to be Z. So Z. Now let's move on to the next one. This is way simpler because hydrogens are entgegen, that is opposite to each other. So again it's going to be E, right? So far ZE, ZE, that is what we got. Now let's check for this. We have hydrogen here, COH. So this will get higher priority and here also this will get higher priority. They are on the opposite side. So what about this? This will be E. Right? So we got Z, E, Z, E and this also will be E. Right? We have answered the first part, that is we are supposed to identify the configuration of the double bonds. Right? Now, how many stereoisomers are possible? So for the total number of stereoisomers, we generally use the formula 2 to the power n, where n is equal to the possible whatever configurations are there for the molecule. Now 1, 2, 3, 4, 5. We have 5 double bonds. Therefore n is equal to supposed to be 5 because n refers to the number of double bond which can form different isomers, that is EZ. That means what? When I twist this molecule, it can form Z. When I twist this double bond, right? When I rotate this single bond basically, right? This group will go this side. So again it can form E. E can become Z and E can become Z, right? So just by rotating the bonds, there is a possibility that you can change the configuration for these double bond. But if the double bond is inside the ring, you can't rotate the carbon-carbon single bond and make it as E. Remember, this double bond cannot be changed to entgegen, that is E configuration, because the double bond is a part of the ring. That is what is very important here. That is the deciding factor whether you will get the right answer or wrong answer. Okay, although we have number of double bonds as 5, no, we can't take 5, we have to take only 4. The 4 double bonds what we have here, they can change the configuration but not the double bond present in the ring. Therefore, how many stereoisomers are possible? So you have to use the formula 2 to the power 4. So the total answer would be 16. Right? So this is how you have to identify the configuration and you can predict what are the total stereoisomers possible for the given molecule. Thank you for watching this video. I hope you have understood this concept. If you have not, you can always ask your questions in the comment box. Thank you.